The final wise Zoominar of this year. We're going to be speaking about waves in extreme conditions, and we're excited to have two speakers with us today. We have Momme Hell from NCAR to kick us off, and we have Tryve Halsne from Met Norway and University of Bergen as a second speaker. And this time around, we also have online contributions, contributions from different time zones. So there are two online talks, one by Carolina Karmichanov. Fortunately, she's not here to correct me, and Gusela Grossman-Matteson. And if you go onto the YouTube channel, you'll find their recordings available as of now. I'm going to stop sharing, and I'm going to hand over to our first speaker. So, Momme, if you'd like to share your screen.
Share my screen first. Okay.
And go full screen. Perfect.
See what you're supposed to see, I guess.
This is looking good. Yes, indeed.
Okay, yeah. Thanks for inviting me. I'm Momme Hell. I'm currently a postdoc at NCAR. Before I was at Brown, and before that was at Scripps. This is work I did at Scripps with two of my French collaborators, and it really comes from this situation. It's the view from my office, just to make everyone a little angry. This is an atypical day at Scripps, where you see long swell coming in Southern California, and at some point you really ask yourself, where does the swell come from? Why do these people not work? Instead go surfing. But if you ask actually where does the swell come from, you run into common theory that I think that I will allude on here more in detail. And I actually try to understand better the processes of swell generation by storms, and then also this has some impact on air-sea interaction because storms have normally very strong wind conditions, right? So, and that's the problem here, that like we know that swell come from storms, but under storms it looks roughly like this, right? You have very nonlinear sea, right? You have very sparse observations, and it's hard to verify the wave height under storms. And we know that many flux coefficients under storms are uncertain, and that's why the study has, besides and like having an impact on our theory of swell generation, it also has some implications for actually climate modeling. That's what I'm doing right now at NCAR. Right, so the basis for this is the fetch relations you all have probably seen before, right? You think about winds blowing offshore, so that at the shore you have no waves. And then for over some distant x, a constant wind speed u10 blows over the ocean surface. And then at this position here, you can estimate a spectrum S that only depends on these two parameters. You go down the Jones-Swab machinery, and you can generate a Jones-Swab kind of spectrum that looks like this. And as you grow further offshore, your spectrum will grow, right? And the problem is now that in this assumption here, you have a constant fetch length and a constant wind speed, but that's not what the open ocean looks like, right? If you look at the Southern Ocean, for example, you have all these low pressure systems that sit there and somehow make swell, right? It's a continuous problem. Winds vary in space and time all the time. And I'm illustrating here on the right the wind patches under storms, and you see that's these wind patches, that is what makes the swell, and that is far away from the static fetch relations that I introduced before, right? And then I can ask the question, what does fetch actually mean in the open ocean? How do the cyclone dynamics are related to swell generation, and how does then in the climate question, how does storm track variability affect wave generation statistics? What I try to put forward here is this Lagrangian model of swell generation. You see here a low pressure system with a big low in the center, a cold front and a warm front. And I'm mainly concerned with these typical high wind patches behind the cold front. And that's the model I will work with throughout the rest of the talk. The talk has two parts. Part A is a forward model where I introduce this Lagrangian model of swell generation, and the B, a backward model where I introduce a big inverse problem to validate my theory. What I'm trying to do here is I try to compute wave growth in this moving reference framework. So I can write down a single equation for the peak frequency, WP, omega p, right, that comes from Kudryavtsev and also from Hasselmann, and that's already in the Lagrangian system. That means I'm looking at wave growth in the system that moves with big V, which is the translation velocity of the storm. And I'm simplifying this in this 1D equation, right? So big V goes to the lower right, and I'm looking at wave growth between these points A and B, and they move with this moving window, so to say. And then I solve this equation for the peak energy or the peak group velocity, right? Whatever parameter I want, basically, based off the methods of heuristics. But the actual parameter that I'm solving for is omega p, the peak frequency. And then we can plot these Hofmüller diagrams kind of thing. So we have the points A and B that are sitting here in the x-axis, A and B, and then the vertical axis is time. And this, if you understand this graphic, you will understand most of the rest of the talk, so I spent some time on it, right? The methods, the characteristic curves are these banded curves here, and the thickness illustrates the group velocity, essentially, right? And what they mean is the following, right? When we start at a C at rest, somewhere under this moving patch, this moving box, the waves are small, so they're slow, and they will propagate backwards in this moving reference system, right? That's why these curves are banded to the upper left, right? The wave energy is moving backwards in this moving box. However, since the winds continue to blow, and will lower the peak frequency, the group velocity will rise until a point where the group velocity is the same speed as the translation velocity, big V, right? I'm calling this a trapping condition. Some people might call this a resonance condition. I'm going with a trapping condition. That means in this case, waves and the forcing move with the same speed, and they're basically locked in. And the only way how to leave this situation for the waves is to grow further, right? They have to further accelerate and move to the front of the storm, which would be then somewhere here at this vertical line. And then they can leave the storm itself, and then they can also stop growing, right? But this is essentially a grow or die process where you either grow until you're at the end of your forcing, at the front of the forcing, and then leave the storms at the front, not in the back, right? And then you can just geometrically, you can solve for the longest characteristics, which would be then the longest waves that are generated. And all waves that are leaving behind this green point here, which is this green bar, would have the same characteristics. Now you can, of course, change the parameters. There are 4 free parameters: the translation velocity, the wind speed, and the storm size. So you can, for example, go to the right and say the storm is shorter, but otherwise have the same characteristics. The storm is shorter, but has weaker winds. That means the bending is slower and the whole wave growth process is slower. This would be then a time-limited situation, where the longest waves are appearing at the end of the lifetime of the storm. Or you can generate a tropical cyclone that is way shorter in distance, but has more intense winds, and that's a very effective wave maker, that once the trapping conditions and equilibrium is reached, you will just generate waves and shoot them out at the front, right? Again, this whole system is moving at the same time, right? So the origin at the open ocean will be not at the same point, it will be as the system is moving. Now, winds are not a box, or winds are not blowing in the box, right? Winds are continuous, as I said before. That means I have to make this model 1 point more complex, and that is, I'm now replacing my constant wind by a Gaussian wind field, and the only requirement is already that the winds are at the corner of this box are 0, and in the center they are not 0, and then you essentially end up with a Gaussian wind blob. You can play the same thing again, right? You create characteristic curves. The coloring is just for illustration. And in this case, you see the trapping condition is not reached. The forcing is too weak. The blob is just moving over the surface, making some waves, but the waves are always left behind. They never can catch up. You keep the same characteristics, which is roughly the typical characteristics of a synoptical system, right? But then have a higher wind speed of 20 meters per second. Then you reach a trapping condition. That means you create these bendings, right? And then you create something other interesting, which is this one, right? You create caustics of these characteristic curves. And these caustics are indicating a very interesting physical process, which is the spatial convergence of wave energy somewhere where not the highest wind peak is, right? So in other words, right, the highest winds are here, but the convergence of this wave energy due to these differential velocities is here, right? That we would expect here still the waves to grow because you add more energy for a given area. That probably means you enhance wave dissipation and also wave-wave interaction, right? And to get this trapping condition, the only thing you need is this gradient here, right? You can think of any other form of winds, but what really matters for get this bending of the curves of the wave trapping condition is this gradient on this side of the winds. Another comment I want to make is the comment on wave H. You see the same stuff as before, but in a little video, but now on the right side, you see the group velocity, and as these different characteristic curves reach the trapping condition. And then you also see wave H for the different colored lines. And if I let this run, right, this process as before, for cases where the trapping is reached, that is somewhere here, right, the curves are bending, you get the convergence, and more interestingly, you get this other situation, or you get these two different C's, because you have a young C, which is everything until you trap. So this is the area here, where fetch relations are probably good descriptor of what's happening, and wave H is also a good descriptor of that. But then you have a mature C where the winds are weak, but the waves are old. That's why I call this mature, right? Where these simple relations between group velocity and wave H probably not valid anymore, and you really shouldn't use wind speed as a tracer for your group velocity, in other words, right? So that's a hint at like that parameterizations there will break down. Or wind speed based parameterizations will break down. So what I showed you here is three things, right? First of all, there's a peak wind speed, but that's not where the highest wave energy is, or that's not where the most nonlinear action is. That's probably here where the caustics are. And then there's a third point, which is where the linear swell appears, right? Because as long as you have nonlinear wave interaction, swell cannot really form and cannot really disperse. But once this process settled down, right, once this system here equilibrates, you will finally generate swell. Then you have the classic dead swell propagation that will be important in the second part of the talk. But what I identified here is basically these three different areas. Okay, that leads me to part B, which is the backward model. And that is concerning with this part here on the right, right? So I'm proposing basically a source area of swell that is ahead of the quote front and away from the highest wind speed. And from this small source area, you have radiating waves going like dispersing. And this is a quite old problem, right? And I'm illustrating that here with this animation again. You have different seeded buoys in the North Pacific by color coding. And this is the spectrograms at these seeded buoys. And each of these black dots is a swell arrival that's identified by some algorithm. And of course, you can then ask again the question of the first slide, how do these swell events are related to the storms in the open ocean? I go back, right? And so there's a storm, a low pressure system coming in. It makes high wind speeds and therefore waves. And then how do I say this particular storm or the next one is related to these events here on the right? That's a very old problem. That's tracking storms by forerunners of swell from Walter Munk. He did exactly the same analysis for D-Day or like for the Normandy landing for Second World War, right? And I'm playing the same game, but I'm tracking peak frequencies and spectrograms and try to figure out their origin. You can do this when you know that longer waves travel faster. That's a deep word dispersion relation. And you can create this set of linear equations where when you assume that energy comes from a single source somewhere in the open ocean at T1, and then you assume that lower frequencies travel faster, that's F1, then you will see at the distant location like this dispersed curve. And from that, you can actually again graphically solve for the two unknowns of these linear equations, the origin time at the radial and the radial distance. You can build this now in a totally parametric model where you radiate waves somewhere at an origin point, and that's at the origin point, and then you will see how these waves appear at these different stations. These are my wave buoy locations, And the panel on the upper right is the wave energy or the parametric wave energy as it travels with a peak frequency, right? This is again a Lagrangian view of point. And then these other points are the seeded buoys where you see the same energy appearing in their dispersed form. And the radiating circles you will see here are the forerunners, right? The 1%, the 5% of this points of this swell energy radiating out of this point source, right? And that's how it looks like, right? Oh, this thing should actually bend. It doesn't. But as this, right, you see that, for example, this buoy here, you see is quite dispersed curve that looks like this. And this is what I would expect in my observation. And when I can create this forward parametric model, I can also pose an inverse problem from it, right? By basically asking, what are the parameters? What is my origin point? So that these arrival things match well with my observations. The model I'm using here is essentially a conglomerate of known theory, right? So I use the Johnson spectrum in frequency space, and there are three parameters, which are these blue variables. Then I use a K-gamma distribution for time, which is a bit made up. And then there's a linear attenuation that comes from around 2009. And all I'm doing, I'm optimizing for the position in the open ocean, as well as all these parameters in these functions. And what you then get is, by using some Monte Carlo sampling techniques, the most likely origin of swell events in all 5 wave buoys, which you see here, right? And you see that this point here, this black dot, this point in space and time, seem to fit the best 4 of these 5 observations. So all the observations ahead of the storm. So, and it doesn't fit well in the station in Hawaii, right? That's basically in the other direction, right? There's a mismatch of travel time of about 6 hours. So the model works where it should work, and it kind of doesn't work well where it shouldn't work well, right? But the actual question is, why does this work at all, right? I just showed you, or we all know, that waves should originate from a longer process under a storm that takes a few days, right? And a long spatial extent. But I'm here successfully identified the single origin point for swell. You can also solve this in another way. You can solve this in a brute force way. That means I'm sampling the whole space of likely origins and times, and then I get something like a density map of wave origins. And that's this green circle or this green ellipse here, which is one of the most likely origins, or which circles the most likely origins for a given time. And I'm plotting here the winds in the same time slot again. And you see the highest wind speed, it's actually sitting here rather than where the most likely waves are. If I propagate forward in time about 12 hours, I think, then you see a similar thing. The most likely origin of the swell is here again, but the highest winds that are closest to that is this one, right? And by just tracking the most likely origins over time, you get a trace. You get these green dots here, a trace of most likely origin in this 3-dimensional space. And what I'm trying to show here is, I'm just showing you the same data in a video, that the most likely origin of waves is actually systematically ahead of the highest winds, right? So I'm making this a little slower. The highest winds are the red area, and the green dots are ahead of this. And they're leaving this green trace here. And then I can actually take a section through my wind data along these trace of most likely origin and go back in my 1D parametric model space. And then it looks like this, right? So the most likely origins are here, and the green dot here is the Monte Carlo method. And this red dot here is the highest wind speeds along this trace in that direction. And then I actually can construct a simple 1D model from the first part that matches roughly my observations. And I'm taking this basically as a confirmation that the swell actually originates not from the highest wind speeds, but from the area where the caustics, so to say, die. Right? And what this puts forward is like, I can use this eyeless Gaussian wind model to translate the fetch relations to continuous wind data. I can explain how swell is generated by a moving storm with continuous or with smooth winds. And I can identify source locations towards the storm that are actually not where the highest winds are. So, and to conclude, I gave you a comprehensive explanation of how swell systems are generated. I presented you a sufficient minimum model for swell generation in the open ocean. I connected swell events with storm characteristics. Right now, I can actually predict where the swell should originate, what amplitude it would have based on few parameters, namely the speed of the storm, the length and the timeline of the storm, and the peak wind speed. And we know that we somewhat have an idea how these things will change with global warming. And I showed you that the spatial wind gradients are important for trapping and creating these non-local effects. And with that, I take questions.
Thank you very much, Momme. That's a great talk. Let's see if we have any questions from the audience. So if you have any questions, you either just unmute and turn on your camera and start talking, or you raise your hand, however you want to do it. So let's see if we have any questions. The summer is clearly already in the heads of many people.
I have maybe a question.
Yes, please, Romain. Yeah.
Yes. Hi everyone. Romain. Hi Momme.
Hello.
I didn't quite understand how you estimate with the brute force the origin of the swell from the second method. If you could just
yes.
Repeat that.
So to optimize this, function, I have a cost function, right, which is basically the difference between these parametric models and my data. And then I'm asking, when I'm basically asking for each point in the North Pacific, what is my cost? And I'm repeating that each time step. And that gives me a cube, right? It gives me an XYT cube of costs. And that's basically a likelihood.
Right, because you're doing that with several different frequencies.
No, I'm doing this with points in space and time, because right, the whole thing relies on deep-water dispersion, right, on this curve. I'm basically asking, right, if I'm here, what are my slope lines at the wave buoys? And then if I'm here at the time later, right, I'm moving everything in time. So I'm just sampling all possible combinations.
Right. Okay. Thanks a lot. Very clear.
Thank you, Romain. There's a question from Daniel Hauser.
Yes, thank you. As far as I understood, this method is valid only if you have trap wave conditions, right? So what about the other conditions?
Good question. So if I go back to this, right, in this condition, you wouldn't have a focusing, correct? And yes, I assume that, but I think most storms trap waves. And
well,
also, like, yeah,
depends on the propagation speed.
Yes, exactly. It depends on 4 parameters: peak wind speed, propagation of the storm, and size of the storm, and lifetime of the storm. And of course, the parameters in my model. So there's of course like classic like other uncertainties in this simple model, which come from there. Yeah, they're in the equations.
Thank you.
Okay, thank you, Danielle. And do we have any other questions? Oyvind, please go ahead.
Hi, Momme. Very nice presentation. I'm actually outside. I'm out driving, so if the audio is bad, please let me know. I have a question regarding your backward computations. It's a linear problem, in which case it should work. How non-linear can it get? if you catch my drift, when is it going to break down your backwards computations?
It's technically a linear so like this simple version, this one is linear, right? Where Watermonk's thing. It's getting, and you can probably write down the situation for all origins, but I treat it as I treat it as a nonlinear optimization. So I just optimize, right? I don't care what the problem is. I just minimize the cost function. The theory breaks down when I'm not really sure how to answer if something other happens to the waves than linear propagation, then the theory breaks down. So yeah, I'm from the origin to my observation, I just assume very straight, boring lines.
Right. The other question I have regarding your linearity is that you're just assuming that you're propagating swells backward, right? So you're not saying anything about the nonlinear interaction and the way swell is actually generated by the storm. Does this explain why the point of origin is always at the front of your storm system?
Yes. So that's what I did all of this, right? That's what I did this backward propagation to prove. That's what I try to prove here is I get a point that is systematically different than the highest wind speed. It's hard to see.
Right.
So the highest wind speeds are here, and so there's this constant distance that moves over the surface, and by assuming waves as swell is boring, I can identify this point of origin, which is not the highest wind speeds. So that's what I try to prove, and that's what I also predict with the forward model.
Yeah. Okay. So good.
Both models together have a consistent picture and make sense. So that's what yeah.
Okay. Thank you.
Great. Any final questions to Momme? Thank you, Momme, for a great talk. Let's then switch to the second presenter. So Tryve, if you want to share your screen. And in the meantime, for those of you who arrived late, please be aware that there are also 2 online contributions, and you can go to the YouTube channel and you can watch them after this talk. The next speaker is Tryve Halsne from Met Norway and University of Bergen. Tryve, take it away.
Yes, thank you. I guess you see my screen. I'm sorry for the margins at the sides of my screen, but they're there. Well, thank you I would like to say thanks to the organizers for setting up this meeting. I'm presenting here, so what you see here is not the view from my office, but it's the view of the ocean as it was in the 16th century. But I'm presenting here a talk that's called Wave Modulation in a Strong Tidal Current and its Impact on Extreme Waves. So this is work that I've been doing together with colleagues in Italy, Alvisa and Francesco, and colleagues at Met Norway, Kai, Anna, and Oyvind. And the map that you see here is the Carta Marina by Olaus Magnus, a Swedish priest from 1539. So it's the first nautical map covering Scandinavia, actually. And you see Iceland to the upper left, and to the right, you see the coast of northern Norway. And the strong tidal current that we're going to look on today is the Lofoten Maelstrom. So many know the word maelstrom, and it originates from this area. So the first part of the word, the mal, comes from Dutch. It means grinding, or in some contexts also pulverizing. It refers to these giant creatures that apparently were left at the bottom of the sea to make the water salty. So they were grinding salt at the ocean floor, and they generated these large eddies. So it's known as powerful or violent whirlpool in the sea, or a situation or of confused movement, or some kind of turbulent situation. And this is how Olaus Magnus depicted it back then. So a more recent painting of the maelstrom, still historical, was made by the Italian cartographer Vincenzo Coronelli in 1690. And this is directly translated from Italian using Google Translate, saying waves formed by the sinkhole of Muskströmmen. So Muskströmmen is the Norwegian name of the maelstrom. And what you see here is, so you see a ship in the middle, and you see the waves that were thought to appear in the middle of this very strong tidal current. So apparently they were known to become very large. And another historical account is the one from Anders Arebo, a Danish priest, saying that the maelstrom generate waves so high that they obscure the view of the sun. So we'll see in this talk if we manage to get waves so high. So the Lofoten maelstrom is one of the world's strongest open ocean tidal currents. You see the map to the lower left in the corner. It's located in northern Norway, at the edge of the Lofoten Peninsula. And it goes in and out in the picture that you see here, in and out between the island of Musken and Lofotodden. It's a beautiful area, by the way, but it has very strong currents. It reaches speeds of at least 3 meters per second, and some accounts also up to 5 meters per second, but such high speeds have never been verified. It actually has, so it's about 8 kilometers between the island of Musken and Lofotodden. And it's estimated to have a higher volume flux than the Amazon River. And it's a very important dynamic component for the local ecosystem, or the non-local ecosystem, because this is one of the main areas, spawning areas for the North Atlantic cod. So they spawn in this area, and then the egg and larvae gets advected out by the tidal current and propagate northwards to the Barents Sea. So essentially what we're looking at here is we have this very strong tidal current that you see to the left there. This is the ROMS implementation at 800-meter resolution showing the surface current. I'll introduce you to that more in detail later, but we have this strong tidal current, and we have some kind of wave field or a sea state. And they interact, and we want to see what's the impact on the expected short-term extreme waves in a space-time framework. So do they really get so high as Vincenzo Coronelli predicted back in 1690? So we're using a space-time framework that is, if we consider the sea as, or if we measure the single point, in particular if you have a broad-banded sea state, you're most likely not, you will most likely not capture the highest waves from a single point observation. So the highest wave might be 1 meter from you, or 10 meters, or 30 meters, or whatever. But the thing is here that you extend, instead of kind of considering a single point, you can extend this area to a space. So you get kind of a space-time domain, and you can want to kind of estimate or get an expected value of the highest waves you might encounter in this space-time domain. So the question that we're trying to answer here is, if you're sailing in the maelstrom at a given time, what is actually the highest wave that you can expect to encounter? And how does this current influence these statistics? So we'll start to look at how currents modulate the sea state, and the framework that we're using here is the wave action balance equation. So we're looking at phase average models. And the wave action balance is the equation in the middle here. So it has a left-hand side and a right-hand side, and we're primarily interested or we've been kind of looking at the influence of currents in the left-hand side of the equation, kind of looking at the wave kinematics. And we're considering a quasi-stationary current. So you see here where the current enters the equations. I won't go into details on everything, but essentially you have a advection term, the x dot, and a change in the wave number vector. And the current kind of enters the equation. So we haven't touched the right-hand side we used. You can also, there are parameterization that allows for currents into the source terms, but we haven't done that here. And also, assuming a quasi-stationary current, the change in absolute frequency omega dot is 0. But if you're interested in looking at modulation by unsteady tides, Alison Ho gave a very nice wise Zoominar last year in January 2023. So you can go and have a look at that talk. Looking at the wave kinematics, variable currents, they may change the direction, they may change the amplitude and frequency of ocean waves. And here I'm showing you two important mechanisms that we will consider throughout this talk. So the one to the left is current-induced refraction. So here you see a current field from above, and you have these wave rays propagating on kind of following and opposing a current jet. And here the change in direction is kind of a local thing, so it happens where you have the current gradients, but the change in wave amplitude or wave energy is non-local. So typically you have convergence of wave energy, a buildup of wave energy within this orange boxes where they converge, and where they diverge is the opposite. A more of a local mechanism is the one to the right, which I have called here the wave straining mechanism. So that's the solution by Longway, Higgins, and Stewart from 1961. And the typical situation, if you have opposing waves and currents, the wavelength will shorten. And in order to conserve wave action, you need amplitude energy to go up. So shorter waves and higher waves. It's more of a local mechanism that happens where you have the current gradients. So this is my most busy slide, and I'll try to talk you through it because I think this is kind of relevant and important here. So what you see to the right here is, or all the figures that you see here are from Arduino et al. 2017. So Romero et al. 2020, they did a similar analysis. But what you see to the right is on the x-axis, you have the scales of variability and we're only considering here the colored lines, the M0 to M4, that's the spectral moments. And if you look at the figure at the bottom, you have two model runs, wave model runs, one including and one not including currents. So the one to the left is significant wave height, which is proportional to zero order moment with current forcing. And what you see to the right is kind of the energies, or kind of the scales of variability of these different spectral moments. So at larger scales, and to the left here, there's most energy on the zeroth order moment, and it kind of decreases the higher the spectral moment. And these are associated with different C-state parameters. But if you go to the shorter scales, there's kind of a transition range where you have more energy on the higher order moments compared to the lower order moments. And if we look at this through a unidirectional spectrum, we can kind of think of the spectral moments as weighting different parts of the frequency spectrum. So the higher the moment, the more do you weight in the high frequency part of your spectrum. So the zeroth order moment is really targeting the energy carrying frequencies in your spectrum. While if you go to higher order moments, they kind of weight more the higher frequencies. And then this parameter to the lower left becomes important. So that's the current speed over the group velocity. So if that one is small, you have kind of less local modulations of your wavefront. It's less sensitive locally to the current gradients. But if it's high, then your waves, the high frequency waves, are more kind of sensitive to the ambient current. So essentially we can look again at the picture to the right here and say that at larger scales we have kind of mechanisms like current-induced refraction are the dominating is kind of the dominating mechanism at the larger scales, where if you go to the shorter scales, the local modulation mechanisms like the wave straining mechanisms become more important. Okay, so looking at short-term extreme wave statistics in a space-time domain. So here I look at the expected maximum crest height for a given C-state. So, and this is kind of a composite of different C-state parameters. So the expected value here is the overbar. So eta max space-time denotes the expected maximum crest height, typically normalized over the significant wave heights or over the C-state, which is proportional to the zeroth order moment. And it has some kind of functional dependence. So it can be computed from the directional spectrum for a number of variables. But here, I'm not listing everyone here, all of them here, but the key parameters that we found is the spectral steepness. And the steepness is kind of a measure of the nonlinearity of your C-state. So increasing the steepness, your crests get higher and the troughs gets wider and shallower. So it's kind of a measure of the nonlinearity of your C-state. And this is proportional to the first order moment squared or over the zeroth order moment squared. And then you have the N3D parameter, which is essentially the number of waves within your space-time domain. So it says something about your sample size. So the larger the sample size, the more waves you can do your statistics on, and the lower the less waves. And also here, Francesco Fedele had a very nice wise Zoominar November 2022, which also is available online. So 2 points here. And the first one is that the current new horizontal variability in expected extreme wave crests may not follow that of HS. So we often think about that the currents kind of dominate the horizontal variability of HS, and we might think that, okay, all the other C-state parameters follow that of HS, but it's not necessarily so. And also that the underlying interaction mechanism may not equally then modulate all these C-state parameters, and we'll take a look at that here. Okay, so turning back to C-state modulations in the Lofoten-Malmström. So our setup in this study was that we have an ocean model, that's ROM's 800 meters surface implementation running operationally at Met Norway. So here you see the surface current to the left. Then we have a wave model, a WAM 4.7 model, also at 800 meter resolution, where we add, so we typically have wind forcing, but we add currents as forcing. So it's denoted W plus C. We have a wave model with wind forcing only, and to the right here you see the difference. The difference here is in the significant wave height. And I would like to highlight also that the new implementations of, or in Wayward 3 and in the new recent implementations in WAM, you can get the expected space-time extremes as output fields. Also in the Malmström, we had the measurement campaign for 3 months in 2018 and 2019, where we deployed a signature 500 ADCP. In the Malmström, you see the screen point here, where we were able to measure currents and waves simultaneously over a certain period of time. This data are reported in Satwa et al. 2021 and Halsne et al. 2022. And we've been looking at 2 characteristic cases. So these are very idealized here. So case C2 to the left is that the Malmström, or Muskströmmen, the local name, takes the shape of a narrow kind of tidal jet when it goes out like this, when it kind of goes towards the west. And in this case, you often have a swell coming from the west. So typically a swell opposing a tidal jet situation. And the other case is that you can, when the Malmström goes to the right here, it is more broad and more uniform in its extent. And in this case, you can also have a local wind sea from the east, and it's land further east, so you won't have any swell condition here, but you can get some local wind sea. So starting with a C1 and looking at the C-state modulation, so the figure to the right, I'll take you through panel by panel. So this is the time series on the x-axis, and the upper panel is significant wave height. And the blue line is the W plus C with current forcing, the orange line is wind forcing only, and the green line is the observations. And you see that when the blue line goes up and when you have a gray background is when the wind sea and current are opposing. And you see that there's an okay agreement between the model and observation. You see for this particular first gray vertical bar that there is a mismatch, and that's actually because we have a bimodal C-state, so there is some swell coming from the west. And you see that from the spectrum to the left, that there is a bimodal C-state, and the current actually turns sometimes before in the observation than it does in the model. So that's why you have this shift in this first peak. But there's an okay agreement, I would say, on the middle peaks, which is quite fascinating actually in a strong current like this. And then the second panel, panel B, is the spectral steepness. Again, an okay agreement. There are some spikes here and there, but it's an okay agreement. And panel C is the sample size parameter. And you see that also goes up during opposing wave and current situations compared to the wind-only simulations. So if we compare this with a theoretical solution for the wave straining, so I'm sorry here, the colors are not kind of showing the same, but I'll try to explain it. So to the left here, the orange line is equation 7. So that's essentially solving this wave straining mechanism for epsilon for kind of the same time series. So that's computed in this orange line. And the reason why they get so high is that you don't have any dissipation in that model. And then the black line to the left is the intermodal ratio. So that's the steepness between the two models, the W plus C over the W. And then since it's the bimodal C state, the green ones are only the wind C part of the spectrum. So you see that there's an okay agreement. So we kind of chosen the peak values from the spectrum and find that it's kind of fairly good represented by this model. It overshoots every now and then, but it's fairly represented. And if we then look at the expected space-time extreme crest during this case 1, that's the panel A here. You see, if you look at the solid lines, those are the ones with epsilon, where you allow for epsilon corrected to second order. And the dashed lines are the linear ones with epsilon equals 0. But if we focus on the solid lines, we see that during opposing waves and currents, the expected maximum crest height, which are normalized by the significant wave height, they increase during opposing wind C and current. And we find a 0.92 correlation between the expected maximum crest heights and the spectral steepness. And we found that this sample size parameter, the N3D, didn't play such a dominating role, because there is a lot of waves already in our space-time domain. So if we increased it a little bit or decreased it, it wasn't very sensitive to that parameter. If we jump to this other situation now, where we have the swell opposing the tidal jet, we find that current-induced refraction really caused this caustic, so there are focal points in the middle of the current jet. So what you see to the right here is wave rays, just idealized wave rays from an open source solver that is overlaid the significant wave height map from the W plus C, where we add the current forcing field from our simulations. And the blue arrows here are the peak frequency. So it's kind of a consistent pattern, and it's kind of the jet is so that the currents really get eaten by the jet, and they focus in the middle of the jet, and we find a significant increase in the wave heights to up to 90% from 2 to 4 meters in the model run. However, at this slide we didn't have any observation, but this is what the model tells us. And if we look at the C-state modulations, so on the right here you still have a time series, and in the upper panel you have the significant wave height. Again, the blue ones are with current forcing, and the orange one is without current forcing. And the panel B here is the intermodal ratio. So the black line here is the steepness when we add current forcing over the steepness without current forcing, and the brown line here is this simplified wave straining solution for this kind of local modulation for the spectral steepness, and yellow here denotes that the intermodal ratio almost always exceeds that of the simplified solution. Again, in panel C, we find that during opposing waves and currents, the expected extreme wave crests increase when currents and wave are opposing. And we find also here a very strong correlation between expected extreme wave heights and the spectral steepness. Okay, so in order to do a summary of these results, we find that the strong current, the Lofoten-Malmström, really has a substantial impact on the sea state. And we find the space-time extreme crest to increase up to 15% during opposing conditions. That's compared with model simulations without current forcing. We find that the extreme wave crest modulation is very sensitive in this case to the modulation in spectral steepness. And at last, we find that these characteristic Met ocean conditions, they seem to control what kind of wave current interaction mechanisms that are at play. So we find that refraction and wave straining to some extent modulate the key C-state parameters differently, and here they are the significant wave height and the spectral steepness. And we find that during this case C1 here, the one to the upper right, where we have wind C opposing a broad uniform current, we find that expected extremes become higher than during the C2 when you have this swell opposing a tidal jet. Even though significant wave height is much higher during C2 than in C1, and also even though the spectral steepness gets modulated much more during C2 than C1. And I'm trying to show that at the bottom here, you see that this intermodal ratio is during C1 in the lower left panel. You see that equation 7 is almost always above kind of the intermodal ratio, while during C2, it's most of the time below. So to couple of conclusions, we find that strong tidal currents generate sea states that are prone to more extreme waves by using a space-time extreme framework compared with no current situations. And we also find that the largest increase in extreme wave crest occurred during opposing waves in current conditions, and that they were very sensitive to the modulation in spectral steepness. So this was published this year in Journal of Physical Oceanography, and I'll leave you there, and I'll be happy to take any questions.
Thank you, Tryve. That's a very, very nice talk. Let's see if we have any questions from our audience. If you have any questions, then simply speak up or raise your hand. Audience always takes a second. In the meantime, let me ask a question. What's the role of resolution of your currents at which they're resolved, the sort of scales that you are including and the scales that you're perhaps not including?
So that is really an issue here. So we know that from satellite imagery, we know that there are very strong horizontal gradients in the current that we're really not resolving in our ocean model. So we're at 800 meter resolution, and we know that the current gradients occur on much lower resolution. So I said here in the beginning that this observation, the current actually turned before the model was able to turn, because it's a very local effect. So we're really not resolving the smallest scales. So we're kind of arguing that we might see something about the trend in the area by using these models that have at 800 meter resolution, but we're really not resolving all the small scale features that
you have a sense from either grid refinement, from even coarser scales, what's the direction of the effect? If you were to be able to resolve finer scales, what would it do to your extreme wave statistics?
Well, I'm not sure. We haven't tested with high resolution. I'm not sure. We're also, if we go to higher resolution, we might start violating the assumption of homogeneity, etc. Which by comparing the observations here with model runs, we're kind of slightly, I think, violating the assumptions already. But we're kind of looking at more the trend here. But I would expect sharper fronts at least going to high resolution.
And can you say some more about your assumption of homogeneity? Because I hadn't appreciated this. It would seem to me that there is no homogeneity in any of this, but okay.
No, so I'm kind of here looking at, well, ambient currents, kind of large scale mean flows. So we have this formalization from listed by Bergen in 1976 here, that the scales of variability of the current, both in space and time, should be much lower than the typical scales of your waves. So looking here to the upper right, we have looking at the kind of stationarity condition. So at the bottom panel here, we're looking at two representative frequencies of the waves given the measured current, because the measured current we have a single point, so we can say something about the stationarity condition, and it seems to be okay. And from the model run with 800 meter resolution, the homogeneity condition seems also to be kind of okay, but still this is at 800 meter resolution, so the homogeneity, the spatial kind of thing, is maybe violated in.
The stronger is the effect of your currents, the more non-homogeneous your results are, and the less valid is the statistical approach. It's sort of
Yes, in particular, if the current gradients are very strong and occur over very short distances. Yeah.
Thank you. Do we have any other questions from the audience today? Looking around, see if there's any hand. Anyone who would like to ask any questions? Okay, well, if there are no questions, we're going to thank both Tryve and Momme for their great talks, and we're going to thank everyone for their attendance, and see you back in the new year after the summer. So have a great summer, and thank you.